So hi, welcome back to Stack Mastery class, where we are going to solve the DSA problem using stack. Now today's topic is sum of subarrays minimum. Okay, so I was actually busy in some kind of work, so I'll make today's video very raw kind of. Okay, so over here, if you take a look, the array contains 3, 1, 2, 4. Okay, now we need to find the minimum of every subarrays. Now, if I try to find the subarrays of this array, okay, this will be 3, then 3, 1, 3, 1, 2, 3, 1, 2, 4. Then we will be having 1, 1, 2, 1, 2, 4. Then 2, 2, 4, and at last 4. Now, if I try to find the minimum of this first subarray, it will be 3. Then this will be 1, this will be 1, and this will be 1. So here you can see that in this subarrays, the minimum is 1. Now for this, it is 1, this is 1, and this is also 1. For this, it is 2, this is 2, and for this, it is 4. Now if I try to find the sum of every minimums, so 3 plus 1 plus 1 plus 1 plus 1 plus 1. So this will be leading to 17. Okay, I hope you got it, that what is the question is all about. Now, how we can solve this? Now, simply what you can do, you can have two for loops in which I will be standing over here and j will be also standing over here. Now you will iterate the j and find the minimum. So for this, the minimum is 3. For this, I mean to say, for this subarray, here you can see that the minimum is 1. Now, for this subarray, the minimum is also 1. Now, instead of iterating again from I to j, what you can do, when you are iterating the j, just check whether it is minimum than the previous one or not. Okay, if it is minimum, then you can keep the counter or you can keep the current minimum and add it to this sum simultaneously. Okay, now let's start. See, here the j is there, so the current minimum is 3. Okay, now I will be adding this current minimum into the sum as well. So sum, initially it is 0, now it will be 3. Now I will move my j over here. I do see that this one is actually lesser than 3. So I got my new minimum, which is 1. Over there, I will be adding this one to my sum. So the sum will be 4. Now I'll move my j, in which I do see that for this 2, the minimum is not changing, right? So I'll just add this one again to the sum only. So this will be 5. What does that mean? So for this subarray, the minimum is 1, and that has been added over here. Now I'll again move my j, in which 4 is not lesser than 1. So I'll keep as it is, and I'll add this one to my sum, so it will become 6. Now I will be moving over here, and j will be where the I is starting. Now over here, the minimum is where the I is pointing, so it is 1. Okay, now for this, I'll again add it to the sum, that will be 7. Then j will be moving over here, in which the minimum is not changing, so it will be 8. Then I'll again move my j, in which the minimum is not changing because 1 is lesser than 4, and I'll add this one again to 8, so it will become 9 now. Now I'll move my I and j where the I is pointing. Over here, the minimum is 2 because this. Now I'll add this 2 into the 9, so it will become 11. Now j will be moving over here. Now over here, I can see that j is 4, where the j is pointing is 4, and this is 2, so it is not minimum, so I'll not change it, and I'll add this 2 into sum, so it will become 13. Now I is pointing over here and j is also pointing where the I is pointing. Now for this, the current minimum is 4. Now I'll add this 4 into this 13, so it will become 17. Now over here you can see that this is the end and you need to return this sum. So 17 is the answer for this. Okay, so I'll write the pseudocode. See, in the question they are saying that this sum can be very large, so you need to divide it, or you need to do the modulus by 10 to the power 9 plus 7. So I'll have this mod is equals to 10 to the power 9 plus 7. So whenever I'm getting this sum, I will be finding the modulo long sum, that will be 0. Now for I equals to 0 to n, in which for every I the current minimum will be a of I. Okay, now for j equals to I, j is less than n, j plus plus. So this is also going from I to n. Now if the current minimum is found out to be greater than a of I, at that time we need to update it. So current minimum equals to a of I. Okay, I hope you got it. Now after that, every time we need to have this sum. So sum is equals to sum plus current minimum. And as we know, we need to always do modulo. So mod. And that's it, we are done. So at the last, we need to return the sum. Now see, here this sum, the data type of this sum is long. Okay, so we need to convert it into the integer. So return, we are typecasting it into int. So I hope you got it about this brute force approach. Now talking about the time complexity of this. So since we are having 2 for loops, so it will be order of n square. And about the space complexity, it is order of 1. Okay, now the question arises that can we optimize this? The answer is yes. See, if I take a look on this example only, in which it is having 3, 1, 2, 4. Now we need to check in which subarrays 1 will be acting as a minimum. Okay, so 1 will be acting minimum over here, and over here. Okay, again over here, and over here. So in 3 subarrays, 1 is acting as a minimum. Okay, so if I take a look over 1 into 6. Okay, now again I need to find that where the 3 is acting as a minimum. So I can see that in only one subarray 3 will act as a minimum, because there are no elements on the left hand side, and if I go on the right hand side, 1 is there. Okay, and if I take this one into consideration, 3 will not act as a minimum, right? So 3 into 1. Okay, now again I need to consider that in which subarray 2 will act as a minimum. Now see guys, if I go on the left hand side, 1 is there, right? Now if I consider this one, 2 cannot act as a minimum. Okay, so only one subarray. And if I go on the right hand side, okay, there is 4. Now over here 2 can act as a minimum, so there are 2 subarrays in which 2 will act as a minimum. So plus 2 into 2. Okay, now the last element about 4. Now over here, if I go on the left hand side, 2 is there, right? So 4 cannot act for this as a minimum. And if I go on the right hand side, there is no element. So only one subarray is there in which this 4 will be acting as a minimum. So 4 into 1. Now if I calculate this, it will be 6 plus 3 plus 4 plus 4. So this will give me 17. Okay, so in this way you are going to find the answer. Now the question arises that, Samir, that how we are going to find in how many subarrays one or any element is acting as a minimum. So for this, I will be taking one example. Now, if I'm standing over here, in which subarray 2 will act as a minimum? Over here, over here, over here, right? Now, if you take a look, if I have 1 in that subarray, 2 will not act as a minimum. So I need to check the boundaries. Okay. Now, if I go on the right hand side also, if I include 7, 2 can act as a minimum. If I include 50, 2 can act as a minimum. But if I include 1, 2 cannot act as a minimum. So we need to check that on the left as well as on the right, where is the smallest element present than 2. So this is nothing but finding the previous smallest element and finding the next smallest element. And we have solved this multiple times in the stack series only. So to understand this approach, you need to watch these lectures. Okay, very important, which is finding the next smallest element, previous smallest element, and finding the next greater element and previous greater element as well. Okay, now see, so the boundary for this is this one and this one. Okay, so if I include this, 2 cannot act as a minimum, nor for this. Okay, now this is the only range. Now the question arises, how we will find the number of subarrays? Over here, we need to count that how many elements are there on the left hand side. So there are 3 elements on the left hand side. Okay, including 2. Okay, including 2. And how many elements there on the right hand side? 3 elements, including 2. So we need to do the multiplication of this 3 into 3. So the answer that I will be getting is 9, and I need to multiply it with 2. So 18 will be our answer. Okay, so in the sum, 2 is contributing 18 times, which is similar to this only. Okay, this is nothing but the contributions only, which is leading to 17. Understood? Now, see, how will I find that where is the previous smaller element using the stack? Similarly goes for next smaller element using the stack only. But how will I find the number of elements? The answer is super simple. If P1 is there, which is this, okay, P1 is this and P2 is this, I just need to do I minus P1. If the stack is empty, okay, if the stack is empty, it will be either minus 1. Instead of P1, it will be minus 1. Now, how will I find the number of elements on the right hand side? Okay, again, it is very simple. For P2, it will be P2 minus I. And over here, if the stack is empty, you need to replace it with length. Okay, again, I'm saying that if you're not watched the previous lectures, okay, you will not understand it. So I highly recommend you to please watch that lectures and then come over here. Okay, now let's find it. See, over here, there is a left array and there is a right array, in which for every element, I'm going to find that how many elements are there on the left, in which till that point, the elements are greater than this particular element. Okay, now I will maintain a stack. Now this formula is for left and this formula is for right. Okay, first we are going to tackle the left. Now see, for this element, for the starting element in which I'm pointing at index 0, the stack is empty. Okay, and I told you that if the stack is empty, in place of P1, you will replace minus 1. Where is I? It is over here. So 0 minus of minus 1. See, answer that I will be getting is 1. Okay, so it means that there are no elements present on the left hand side, but there is one element which is itself. So this is 1. Okay, now every time you need to store the index of that element. So 0, and in 0, 3 is there. So this is only for our purpose. You are not going to store this 3. You are only going to store index in the stack. Now I'll move my pointer in which the value of I is 1. Now see, if 1 is present, 3 cannot be my answer, right? since we are finding the previous smallest element, okay, for this elements, for this remaining elements, if 1 is there in the middle, 3 cannot be my answer. So I need to remove this 3, okay, from the stack. Now the stack is empty, so I need to find the count of the elements. So it will be 1 minus of minus 1. Since the stack is empty, so it should be minus 1. Now it is 2. Now here you can see that there are 2 elements present on the left hand side, which is this. Understood? Now let's move our pointer, but before that, don't forget to insert the index of that previous element. Okay, so it is 1, and in index 1, 1 is there. Now over here the index is 2, right, and we need to find the count, right? So it will be 2 minus 1. Here you can see that on the left hand side, 1 is the previous smallest element, right? So 1 is pointing at index 1, so the answer will be 2 minus 1, the answer is 1. Okay, it means that on the left only one element is present, that itself this 100 it is. Now I'll move my pointer, but before that, don't forget to insert that element. So index 2, in which over index 2 100 is present. Now I'll move my pointer at index 3. Now see, if 3 is there, can 100 be my answer? No, for this element 100 cannot be the answer as a previous smallest element, right? So I need to delete this 100. Okay, but 1 can be the answer. Okay, so for 3 I need to find the answer. Now the value is 3 minus what is the top of the stack, 1, so it will be 2. It means that the count of the elements on the left hand side is 2. Okay, 103. Now let's move our pointer. So first insert this 3. Okay, now see guys, if 2 is there in the middle, 3 cannot be the answer for this element, right? So I need to delete 3. Okay, now over here I can see that for this 2, the smallest element on the left hand side is 1. So these are the count of elements. Okay, and how will I find it? 4 minus 1. How did I got 1? From here. Okay, so it will be 3. So here you can see that there are 3 elements on the left hand side. Now let's store this first. Index 4, over here the element is 2, and move further. Now see, 7, the previous smallest element is present at index 4, so I'll calculate it. So 5 minus 4, the answer is 1. So 1, it means that there is only one element present on the left hand side, which is itself. Store the answer first, 5, and it is 7, and move further. Now if I move further, you can see that the previous smallest element is 7 only, right? So calculate the value. 6 minus 5. How did I get 5? From here. So the answer is 1. So 1 it is. Now if I move further, see, for 1, here I can see that for these elements, for the future elements, 7 cannot be my answer. 2 also cannot be my answer. Okay, so I need to delete this 2. So 5 and 4 is getting deleted. Okay, now I need to calculate the count. So 7 minus 1, the answer is 6. Okay, so I'll write 6 over here. And don't forget to store. So the index is 7, the element is 1. Now let's move further over here. Now for this, the previous smallest element is 1 only. Okay, so let's calculate it. It will be simple. 8 minus 7, the answer is 1. So 1 it is. Now here you can see that for this element to act as a smaller or minimum, okay, on the left hand side there is only one subarray itself, which is this only. Okay, so we have created the left subarray successfully. Now for creating the right subarray, I told you that this is the formula, and if the stack is empty, instead of P2 you need to replace it with length. So over here the length is 9. Now the stack will be cleared. Let me remove this. Now see, for here the stack is empty, So it will be length, which is 9 minus 8. So the answer is 1. So 1 it is. It means that since there is no elements present on the right hand side, so this is the only element present. Okay. Now don't forget to store that element over here. So index 8, 9. Let's move our pointer on the left hand side now. Now for this 1, okay, if 1 is present for this element, 9 cannot be the answer, right? 9 cannot be the answer if 1 is present in the middle. So I need to delete this. Okay, now see, if I'm deleting this, stack is empty. So you need to replace P2 with length, which is 9 minus 7. The answer is 2. Okay, it means that there are 2 elements present on the right, including 1 as well. Okay, now don't forget to add 7 and 1. Now the pointer is this. Over here 50 is there. The next smaller element for 50 is 1, right? So calculate the length or the count. So 7 minus 6. Answer is 1. How did I got 7? From the top of the stack, which is 7. And right now I'm pointing over here at index 6. So 6 it is. Okay. Now it will be 1. It means that for this, there is only one subarray, which is this only. Okay. Because if I include this one, 50 cannot act as a minimum over there. Now, don't forget to store 6 and the value is 50. Now let's move over here. Now for this 7 is there, 50 will not act as a minimum, right? So I'll need to delete this. And after this, I need to calculate the count. So 7, which is top of the stack, minus 5, so it is 2. So here you can see that for these elements on the right hand side, this is a subarray and this is a subarray, okay, in which 7 will act as a minimum. Now let's add 7, which is present at index 5, and move further. Now if 2 is there, 7 cannot act as a minimum, right? So I need to delete 7, which is present at index 5. And now I need to count the numbers, which is there on the left hand side. So 7 minus 4. How did I got 7? As a top of the stack. So it will be 3. Initially, we have counted that how many elements are there on the right hand side. This 3, okay, in which this is a subarray, this is a subarray, and this is a subarray. So there are 3 counts of subarrays. Okay. Now after that, store the index 4 and the value is 2. Move further. Now over here, the next smallest element for 3 is 2 only. So calculate it. So it will be 4 minus 3. The answer is 1. Okay. It means that this is the only subarray. Now if I include this 2 in that subarray, 3 cannot act as a minimum. Okay. So count is only 1. Store that index and 3. Okay. And move further. That means on the left hand side. Now see, for 100, the next smallest element is present on the index 3 only. So calculate it. So 3, which is top of the stack, minus 2, which is where I'm pointing right now. So the answer is 1. And store the index 2 over here. The value is 100, and move further. Now if 1 is present, see, for these elements, 100 cannot act as a next smaller, nor 3, nor 2, nor 7, nor 50, and so on. Okay. So I need to delete all these elements. Okay. All these elements. So I will be deleting this, everything. Now you will be saying, Samir, in the previous, when we were calculating left, okay, at that time, for this, you haven't deleted this one. When you are standing over here for calculating the right, okay, you are also deleting this. Okay, I will tell you that why I need to delete it. Okay, this is a thing that you need to make. Okay, you need to delete this as well. Okay, So if the value is equal to, then also you need to delete it. Okay, only on the right, only when you are calculating for the right array. Now the stack is empty. So as I told you, in P2 you need to substitute length, which is 9 minus 1. So the answer is 8. Okay, now store that index 1 and 1 and move further. Now over here, for this, the next smaller element is 1 only. So calculate it. So 1, which is coming from top of the stack, minus 0. So answer is 1. Okay, so I found all the counts left as well as right. Now I need to find the multiplication. I need to do the multiplication of this. So this will be 1, this will be 16, 1, 2, 9, 2, 1, 12, and 1. After this, I need to multiply this contribution into the array value. Okay, so if I do this, it will be 3, 16, 100, 6, 18, 14, 50, 12, and this is 9. And if I do the sum of all this, okay, the answer that I will be getting is, I believe, 232. No, sorry, 228. Even though I done it in a rough way, so I believe it is 228 only. Okay, I believe you got it. This is nothing but left into right. Okay, and this is left into right. Okay, which is coming from the above only into a of I. Okay, and this is the summation of all this. Okay, so I believe you got it. Now let me write the pseudocode. I know that I am going way fast, okay, but I do have my lectures going on, okay, and due to that I was not having time to record this lecture, so I'm going in a faster way now. Now, if I talk about the pseudocode for this, first you need to create the left subarray. Okay, so how did I calculate the left subarray? Using the help of the stack. So let me create the stack now. So stack integer. I'm doing this in Java. In the question, it was told that the sum can be very large. Okay, so due to that, I'm creating the array in which the data type is long. Okay, now for in which I will be going from 0 and it will be gone till n. Okay, now while first I need to check if the stack is empty or not. st dot is empty. Okay, if the stack is empty, then we can't pop it, right? Anything. So due to that, I have written not over here. And a of st dot peak. I'll check if the top of the stack is greater than a of I. Okay, at that time I need to pop it, because for the future element, that top of the stack cannot be my answer because current element is smaller, right? So st dot pop, and I need to keep popping. Okay, after that I need to calculate the count. So I need to check first if stack is empty or not. Remember, if the stack is empty, the p1 should be substituted with -1, and the formula for that was I minus p1. Okay, so left of I equals to I minus p1. Over here, if the stack is empty, then I need to replace it with -1, and else left of I equals to I minus p1. Okay, I'm so sorry, p1 in the sense stack dot peak. Okay, now don't forget that every time you need to push that index into that stack. So st dot push I. That's it. We are done. We are done with creating the left array. Now see, now I want to create the right array as well. over there this stack should be empty. So I'll call this function stack clear. So it will clear all the elements present inside the stack. Okay. Now long right, in which the size is n, and I will have the same thing, but instead of coming from left to right, I will be coming from right. I will be going from right to left. So I is equals to n, and it will be gone till greater than equals to 0. Okay. And over here, as I told you, that there should be greater than equals to. Okay. Now I will be deleting this and this because I am filling the right array now. So right of I is equals to, the formula was p2 minus I. Okay. If the p2 is, if the stack is empty, here you need to replace it with length. So if the stack is empty, it will be length minus I. And if the stack is not empty, so it would be right of I is equals to stack dot peak minus I. Okay, so this was it. Now I have created the left array as well as the right array. After that, I need to run just one for loop in which I need to calculate left into right. I need to calculate left into right. After calculating this, I need to multiply this value with this. Okay, so it will give me this. Okay, and simultaneously I will be calculating this sum as well. See, like this I'm talking about. I equals to 0 and it will be gone till n. So long contr stands for contribution equals to left of I into right of I modulus mod. Very important because the sum can be very large. Now after this, contr is equals to contr multiplied with element. So a of I mod. Okay, now simultaneously I will be taking this contribution into the sum as well. So sum equals to sum plus contr mod, and that's it. We are done. I believe you got it. If you didn't, I would be advising you to please try run it by yourself as well. So at last you need to return this sum. Okay, and don't forget to have this sum as a long in which the initial value is 0. Okay, now talking about the time and space complexity of this approach, it is order of n, and the space is order of n only, because we have taken the help of the array, 2 arrays as well as stack. So basically it will be 3n only, but approximately it is n only. So I believe you got it. Okay, again I'm so sorry that I was busy in some work. Due to that, I need to record this lecture in a fast pace. Okay, so how it can help to you, you can try run it by yourself as well. Okay, now I forget to tell you that over here I have taken greater than, and over here I have taken greater than equals to. So what if I do not write this? Okay, what if I do not write this? So there is one dry run that you can do for this. Okay, if you do dry run for this example, you will be getting the wrong answer because there are duplicates element present. Okay, for that reason I have taken greater than equals to. Okay, very important. So you can dry run this code for this example. Okay, then you will be getting to know that why did I took greater than equals to. Okay, so I believe you got it. That's it from my side. I'll see you in the next lecture. Till then, keep practicing. Thank you.